Great. So hi, everybody. As Anastasia said, my name is Matthew. I'm a serverless specialist here at AWS. I'm going to kick things off and talk a little bit about SnapStart, a really interesting technology we launched for Java applications running on Lambda. Then I'll hand over to my colleague Richard, who's going to go into a little bit of detail about how you're going to implement that, and he's even risking it with a live demo. So fingers crossed for Richard. So I thought I'd set the scene a little bit about Java, how important Java is, and I know that on this, for this audience, you all know that it's a really significant language, but it's not something a lot in the serverless world. There's been challenges with Java historically, but AWS deeply cares about that, and so one of the reasons we're investing in bigger starters. Java, still is the third most popular language on GitHub. We also see huge demand, particularly in these amazing open source projects, things like Kafka and Airflow, that are predominantly driven in Java. That's really, reinvigorating innovation in the Java ecosystem. So I thought it was an interesting stat. If you look at all the Apache open source projects, every other line of code is Java, and the other half is everything else, and that percentage is growing. And we've seen a lot of innovation, with the JDK, and it's pretty cool that we've got Java 17, Java 20 coming out later this year. Will be Java 21 by the year. It's an exciting innovation that's happening in recent years. One of the things that makes Java particularly suitable for serverless applications is the Java ecosystem has a strong lineage and history in thinking about how to make highly portable applications. So the concept of hexagonal architectures and adapter layers and write once, run anywhere is baked into the Java language, the frameworks. And that fits really, really well with a serverless model where we're looking at making microservices that are very, very easy to compose together when building distributed systems. And one project that is particularly interesting is a project that we build called the Java Serverless Container. So that takes the Lambda model. So typically customers running maybe an API on Lambda will use an AWS API gateway at the front and then have that invoking a Lambda function. That's an evented model. So API gateway emits an event, a blob of JSON that's then processed by your application and responds with some more JSON. The Java Serverless Container works as an adapter layer. So it takes that AWS syntax of JSON and converts it into an HTTP servlet, which can then be processed by whatever framework you want to use. So we've got plugins so you can run it in a Spring app or a Micronaut app or a Quarkus app. And as a developer, you've got a very, very familiar development experience in one of those frameworks. It's also very, very easy to start building an app on something like Lambda. And then if you want to change your mind later because your architectural characteristics change, you can change that adapter layer and go and run it on Kubernetes or on a Fargate container. So one of the things that we have to think about when we are working with Lambda functions is the performance. And the typical performance profile of a Lambda function is that you get most of your requests are very, very fast. So these are what we call warm requests, and they'll respond really, really quickly. But you also get this tail latency. So you get a subset of your requests that respond much more slowly. And I'll talk a little bit about why that happens and what we can do about it. So when we're going to investigate this, we've got a sample project that we put together. It's a Spring Boot application that returns unicorns. So we've got a unicorn controller. It's fronted by API Gateway, and it returns unicorns that are stored in our document database in DynamoDB. So when you've deployed our unicorn service up into Lambda, and there's been no requests at all. The first time it's had requests previously, and it's been invoked and it's warm. this sample application returns really, really quickly. Java's really fast. So within 10 milliseconds, you get a response. That's great. And most of your requests, 99% plus of your requests will be really, really fast. However, if you haven't got an execution environment ready, either because your API hasn't been accessed for the last 15 minutes, or because it's scaling out and we're adding new workers to the pool of Lambda functions, we have to stand up a new execution environment to return those requests. So when that happens, we create an execution environment. That's a Firecracker VM, micro VM. We download your code. So we download maybe a fat jar and put it into the VM. We'll start the JVM. We'll start the runtime, and we'll initialize your code. And that initialization phase can take, on our example Spring Boot application, over 6 seconds. Once we've got our environment ready to serve, we then have to run your handler code. So the first time that your handler code is run, it's not going to return in 10 milliseconds like it does when it's warm. The JVM is going to do a whole bunch of just-in-time compilation, and so actually that first invoke might take a further 600 milliseconds. So the total time for these cold starts might be over 7 seconds. And so that's this kind of lump that we've got in the tail of our performance histogram. One of the reasons that this cold start is longer in the JVM than it would be in interpreted language like Node or Python is that the JVM is doing a whole bunch of work during this initialization stage. So it's doing some class loading. If you're using Spring, there's probably some runtime dependency injection. And one of the reasons that the JVM is so fast, it has a concept of just-in-time compilation. So although you built your jar file, the JVM is still doing all sorts of clever stuff to make sure that it runs really, really fast as native code. Now, for those first few invokes, that's relatively CPU and memory heavy, and so that takes up a chunk of time. There are a number of things that we can do to address that. So when we're looking at solving class loading, we can move from some of our heavier dependencies to some lightweight dependencies. So if we're doing JSON serialization, we might move from the full Jackson library to Jackson Junior. We could try and avoid doing runtime dependency injection. So we could use one of the frameworks like Micronaut or Quarkus that tend to do the dependency injection at build time rather than at runtime, or you might just go to something with no dependency injection at all. And then there are things that we can do to address the time needed to JIT your code. So we can increase the memory of your function, but that does have an impact of cost. So with Lambda, we charge by the gigabyte second. So if we have to add more memory and more CPU in order to get faster startup time, we can also charge you more for it. You can apply something called tiered compilation, which tells the jitter to stop at the C1 compiler, so it's not doing quite as much work to get yourself to speed up the function at runtime, but it's still doing enough to get reasonable performance. And you can also use something like GraalVM to compile your Java application into a native image. So if we look at the sort of typical cold start times we get through those various techniques, if someone just lifts and shifts a Spring Boot application and throws it on Lambda with no optimization at all, you might get 12, 15-second cold start. Quite quickly, by stripping out some of those dependencies, setting an environment variable to add tiered compilation, we can probably halve that, but we're still in that sort of 6-7 second range. In order to get much faster than that, you really have to do some pretty significant changes to your code. So you might have to strip out a framework entirely, or move to GraalVM. And we knew that was a big problem for customers. So back at reInvent in November, we launched a new G called AWS Lambda SnapStart, and that allows customers to achieve 10 times performance functions. And so the way that works is, instead of doing all of that execution environment, doing all of that class loading and dependency injection, jitting, we move that asynchronously. So your pipeline kicks off and it publishes a new version of your Lambda function. We asynchronously, then we snapshot the state of the JVM and the heap. And And then when a request comes into your Lambda function, we'll resume from cache, and then we'll just run your invoke code. And as we have to scale out, because you want a whole bunch of traffic coming pull from that cache, do a resume, and then invoke your code. And that's a huge benefit, not just for performance, but also for sustainability. So instead of doing all that compute CPU intensive work when we scale out the Lambda service, we're just doing that and using all that hard work for every single invoke. So when we do this initialization code, so this is happening without anything being requested, something's happening from your, take this off, we'll download your code, we'll start the runtime, we'll run an initialization handler, and we also give you a special hook, a pre-snapshot hook that allows you to put extra code that you can use to further optimize. At that point, when a request comes in, we'll go and resume a snapshot. You've also got an optional post-snapshot hook, and then we'll go and run your handler. And so with our application, our Spring Boot application, it's serving unicorns, we move from 7 seconds to around a second for that first invoke. And when we speak to customers, 1 second is kind of a magic number for customers. So if you can get that long tail latency down below a second, we can use that for synchronous customer-facing APIs. So at this point, I hand over to Richard, who's going to talk a little bit about how to configure SnapStart and then give us a demo.
Thank you, Matt, for that great presentation and intro. And as Matthew said, we built SnapStart to make to kind of mitigate the problem of cold starts, particularly for Java applications, right? So how do you configure it? I see I need to restart the Zoom here for the screen sharing to work. So maybe you can have the slides on your end while I talk with this. Or let me just restart Zoom here real quick.
I'll move the next slide there for you, Richard.
Yep. Okay. All right. So while I restart Zoom, we can talk about how to configure Snapshot. It's actually quite simple. So the only thing you need to do is to go into the console. And you see there under general configuration, you have an option that says SnapStart. And it says under there, published versions. So what does this mean? So published versions means that SnapStart is only applied to the concept of versioning within Lambda. So if you haven't used this before, we have a feature that you can deploy versions of your Lambda function. And the reason for why we built support for SnapStart into this versioning system is so this actual snapshotting process takes a while to produce. This is because during the snapshotting phase, as Matthew mentioned, we do warm up the JVM, we run your handler code, we then take a snapshot of that handler code, store it in a separate cache, and then when the function is resumed, we restore from that cache. So that's why we need to apply it into a specific version. So when the actual snapshot is ready, we can start directing traffic into that specific version. So we can take the next slide, please. So how do you configure it then? You can, of course, configure it via the console, as we saw in the screenshot. We will also see this in the demo. But you can also use infrastructure as code. So in the sample here, we see SAM code. And you can see here down in the bottom, we have a property called SnapStart. And above that, we have something called auto-publish alias, which is live. And that property is important because, as I mentioned, SnapStart can only be applied to versions of a Lambda function. And that means that we have to automatically publish a version in order to apply it. And again, that other property that you saw close to the bottom there, which is published versions, or I mean apply on published versions, that means that SnapStart is now applied on the versions that get automatically published. So let me see now if my screen share can come up. I think it can. There we go.
Shall I let you take over then?
Yes, please. Sorry about the hiccup. Can you see it? Is it visible, Matt?
Okay, it's yours
great.
now.
Okay, cool. So we can also, of course, apply it on CDK. So in this example, I have a CDK code. I have created a simple function. I added simply the SnapStart property here. And also, similarly, I use the concept of apply on published version that automatically enables SnapStart on the latest version that gets automatically deployed when I create a new version or deploy this stack. So again, create a version and you point an API gateway to a specific version of your Lambda function. As you can see here, we have an alias of prod. That means that that version is being the one that is active and the one that has SnapStart, and we will see this in the demo. It is important because we have to use an alias. We can't just simply use the latest alias, which is the default one within Lambda. You have to provide an alias name. And what you can do with SnapStart also is you can apply hooks and actually hook into the snapshotting process. So this means that you can actually exercise the JVM. You can add more classes that you need to class load and JIT. You can add code. You can even add HTTP calls. So simply put, you can put in resources into the snapshotting process before the snapshot is taken to eagerly initialize things that will be part of the snapshot. That means that on restore, that code would already be warmed up, will be JITted, and is fast to execute. And you can, of course, leverage this, do a loop, execute things that compute heavily, pre-calculate things that you can take advantage of during the warm invocation. Do, however, note that don't put sensitive data in here. It will be part of the snapshot. Also, don't rely on random numbers, secrets, things like that. That is something that we encourage that you do after the snapshot has been restored. And there's also hooks for this as well. As this example shows, registering a hook is very simple. Here I have a simple Lambda handler called hello handler. I implement the resource interface, and this comes from the org.crack.resource package. I register this instance, as you can see here in the constructor. I call core.getGlobalContext.register. And now my hooks are being called at their respective time. So you can see the before checkpoint hook will print to standard out before snapshot is taken, giving me an opportunity to exercise my code. And similarly, the after restore hook is called when the function is being resumed. So let's now see this in practice. So let me just bring out the code in here so we can just see this is a simple Spring Boot application. It isn't any particularly complicated. We have a Unicorn controller. We have a few routes in here. So we're using Spring Boot with route mapping. This usually on Lambda takes many seconds to initialize because this is all scanned during runtime and initialization. So every time a cold start happens traditionally, we have to discover all of these routes and all of the dependencies need to be injected, etc. So with SnapStart then, we can do this once, store all of the initialization information into the snapshot, and then we will have an immediate benefit since all of this code will be exercised already, will be JITted, the dependencies are resolved, etc. So you can see here we have our Lambda handler. This is using the serverless container project. So we simply initialize a Spring Boot proxy handler, set up a few lines of code here. I do nothing else in here, but I have a priming resource. So this is simply a configuration bean. I have a Unicorn priming resource for my Unicorn API here, and I have two checkpoint hooks. So in this case, I actually call the controller to exercise that code with just a random or a dummy ID for my stored unicorns. This means that even though the call will actually fail because there is no unicorn with this ID, I will exercise the code, the methods will be jitted, and they will be part of the snapshot, right? If I don't have this try catch here, it will fail and the snapshot process will fail. So it's important when you do initialization and warm up like this that you keep that in mind. So performance-wise now, let's dive into Firefox here. We can see we have, let me bring up the metrics down here. So if we take a look at the network tab in here, and I start with the normal Spring Boot application with SnapStart off, I hit it, and now we wait for a while here. You can see the GET request to the API. It takes, it's a bit hard to see here, but it took about 4.7 seconds. So for 4,741 milliseconds, which is not great. It's not horrendous, but it's, of course, users don't want to wait for that time. On a warm start, we can see it's very fast. It's 187. And remember, this is end-to-end, of course, right? So inside of Lambda, this is actually way less than that. And you're not paying for all of this time, but end-to-end, we see this results here. Now, actually, this exactly the same code with SnapStart applied. We can see that we're getting 1,427 milliseconds. So about almost 4 times the performance here. Inside of Lambda is actually way less than that, meaning that we only pay a fraction of the cost, and the users will get an instant benefit as the cold start is way lower. And there's no performance impact for warm start. We can see we have exactly the same warm invocations here, even slightly faster as this code has been exercised, more times than the non-SnapStart version one. And if we dive into the logs here, we can see if we go into the slow function here, this is in CloudWatch, we can see the initialization happening with the non-SnapStart version, seeing that, okay, we started the Lambda in 2.5 seconds. The JVM was running for 3.5 seconds, right? It took quite some while to spin this up. And eventually here, we responded with, let's see, report here. We responded in 3.5 seconds plus an additional 530 milliseconds. And this is what we charge the customer. And if we go into the SnapStart version, right, and see the log here, we can see we no longer have this the logs from the Spring initialization, since this is all part of the snapshot. All of this code that's running did run before and was part of the snapshot that we restored. So this means that we only see this last part here. So we only we have now a restore duration and a build duration that is significantly faster, right? So customers will get an instant benefit from applying this. You will deal with the cold start, and you will also have the possibility to warm up the code more efficiently than you can do with other alternatives, right? And remember, there's basically very little code changes required. It's not like I have to refactor my entire application or apply more. It's not as a heavy lifting as doing GraalVM, and this is still running the JVM. So it's still running inside of a JVM. So it's not like we're converting into a native executable, which is no longer a JVM. So you get all the benefits from JIT once it's being warm, but you can take advantage of that at an earlier stage. So now I'm returning back to Matt.
So that is relatively straightforward to configure SnapStart. There are a few considerations we have to think about. The 3 big ones are handling network connections, dealing with ephemeral data, and also how we deal with uniqueness. So, one of the things that might happen with a network connection is that you create a network connection to something like your database service during the snapshotting phase. That can have some performance improvements. However, when you resume it and invoke it, it could be, hours, days, even a week later, that network connection might have failed. And so you've got to make sure that you've got retry logic. So if something does fail, you go and retry that connection. When we're dealing with ephemeral data, we're typically talking about something like pulling secrets from Secrets Manager. So we're doing our initialization phase, we might go and get some usernames, some passwords, some API keys. Again, when your Lambda function is resumed and invoked, maybe those credentials are okay, but maybe they're not. So if you do get an error because you've got incorrect credentials, again, your application should be thinking about that. Probably should be thinking about it anyway, but you might want to go and pull some new secrets if you do see those kinds of errors. Uniqueness is another kind of interesting topic, because we're snapshotting the JVM state and then restoring. Some of the entropy in the VM has been lost. So you have to have some considerations around uniqueness. Maybe if you're creating a GUID right at the beginning of your application, you want to make sure you're not getting any GUID collisions, or if you're generating some seeds for some sort of cryptographic requirements. So AWS, we've gone and verified some really common random number generators. So if you're using java.security.secure_random or OpenSSL libraries, or using devrandom, that all works fine. But you should avoid using the standard java.util.random. And we built a tool that allows you to, an open source tool that allows you to scan your Java applications to see if you're using any random number generation that might be affected by some of the snapshot considerations. So if that is something that you're concerned about, we can help you with that. It's worth pointing out, so some of the results that we're getting through some of the optimizations that Richard was talking about. So if we run a sort of slightly more thorough test, and we go and take our application, we run 100 requests a second through it for 10 minutes. This is we get these kind of latency numbers. Now, this is not the end-to-end network latency. This is the compute latency of Lambda. So actually, that end-to-end, if you run it in a browser, might be slightly longer than this, but it still gives you an idea of the size of the change. So on this application, we got just over 5 seconds of compute time as part of that process. Applying snapshot with pretty minimal changes, we went down to 536 seconds of milliseconds of compute time, and then going and doing additional priming and some of the activities that we talked about, we can then potentially shave off another 80 to 100 milliseconds off the top of that. So by doing that priming, putting some priming in the hooks, we can get down to under 500 milliseconds on this example. And we just thought we'll share a quote from one of our customers. So Capital One have been rolling out SnapStart, one of our launch customers, and they were applying this to a whole bunch of Spring Boot applications, and got absolutely amazing results. So Marty, the VP of Engineering at Capital One, said that really little to no code changes. They got really significant cold start improvements, and it really unlocks a whole bunch of new use cases. So lots of things that are these kind of synchronous customer-facing workloads built on Spring Boot really weren't great candidates for Lambda back in 2022. Now in 2023, with the launch of SnapStart, it really broadens the possibilities for using serverless, getting all the benefits of security, scale, really great pricing model with these vast numbers of business applications. If you'd like to have a go, we've got a workshop. Our workshop covers how to move a Spring Boot application into Lambda. We also look at some other frameworks using Spring Cloud Functions and using some more modern frameworks. We look at what happens when you go and run that with GraalVM, and also some of the implications if you how to go and do SnapStart and all the kind of performance optimizations we can do within that. And so at that point, I think we're ready to take any questions. I don't know if we've got any from the audience.
Anybody left?
Thank you. Thank you, Matthew. Thank you, Richard.